So, Newton's second law of motion. This is a big topic, guys, and it has a lot of aspects to it. So I figured what we'd do is we would start, just kind of, again, with the kind of introduction of Newton's second law, and then talk about how we can apply it to situations that are one-dimensional. So we have a force being applied either in the direction of motion or in the opposite direction from motion, and we'll worry about angles like pulling some stuff at an angle and inclined planes and pulleys and stuff. We'll worry about that later. So I guess to get going, Newton's second law of motion, I'll just go ahead and rewrite it. F net, so this net force, which is a vector, is equal to the mass that the net force is being applied to times the acceleration of that mass. Okay, and so it's very well known. What I want to point out here, though, and it's such a simple little equation, right? It's so very simple, and there's so much to it, is that this net force is the vector sum of all the forces. So, if there's, say, 3 forces acting on an object, you have to add those 3 forces together, but it's not the magnitude, it's the vectors. So, if I have a box and, suspend it, right? So maybe I have, a cable, tied there, and maybe there's a cable, on the ceiling, right there. And, and it's going to, I'm going to change this a little bit so that, so there's this idea, there's a cable right there, and then we have, this force of gravity acting on it. So when we do a free body diagram of this, to give me an idea what I'm talking about with like this vector addition of forces, when we do a free body diagram, we're going to have one force go off in this direction, so maybe force 1, and then another force, kind of going up at an angle, force 2, and then we'll have the weight of the object, or the force of gravity, pulling down. And what I want to do is I want the net force in the object, so I'm going to have to take those 3 forces. I'm going to have to break, each one of these into x and y components. Okay. I'm going to have to add components together. I'm going to add all these together, and maybe, just kind of looking at this, I'm going to have maybe a net force that goes down in this direction. I'm kind of guessing on this one. It does depend on the magnitudes, but say my net force was in this direction. Well, we get that from adding those 3 vectors together. And this net force is what would be in the same direction as the acceleration. And the magnitude of the net force and the mass of the box is what I would use to get the acceleration of the box at that point in time. Okay, now obviously if the box does accelerate downwards and starts to swing down, these forces change and the acceleration will change. But when we do these problems, we kind of like take a snapshot. We freeze it in time. We just consider it at that one single instant. And then we, do our vector addition there. But as I said, we'll wait on the angled stuff later. But I just kind of want to show you what you have to consider as you're working through these problems. So it's the vector, this net force is the vector addition of all those forces. One of the ways that this comes about is when we talk about weight. Okay, so one of the forces that's always around, we've kind of referred to this already, is weight. So we have the weight here. Okay. Now we know that the force of gravity, say this is an object, the force of gravity is going to be acting down. Now, that force of gravity causes an acceleration. We've seen that acceleration. It's the acceleration of gravity. So whenever we need to calculate the force of gravity on an object, we're going to call that the weight. And what we're going to do is we're going to take the mass of the object in kilograms. Okay, we've got to use kilograms for this. So the mass of the object in kilograms times the acceleration of gravity, the value of little g at that point in time. Okay, and then that's going to be the weight. Now, we talked about before the free body diagrams, there's also, I'm going to change the colors here, there's also another force, that's going to push up. It's the force of the surface, right? Now, we call this the normal force. Normal, in this case, what the word normal means is that the force is 90 degrees with respect to the surface. Okay, so it's got a 90-degree angle with respect to the surface, and that's normal force. This is the force that the surface pushes back up on the object with. And here's the thing, okay? This causes our perception of weight. Okay, this causes the perception of weight. So if you were just out in space, okay, and there was no ground underneath you, you could still be accelerating towards an object with the acceleration of gravity, but there would be nothing pushing back up on you. What makes us feel like there's a force of gravity on us is the fact that the floor or the surface we're on pushes back up against us. And if that force changes, we're going to have a different perception of weight. Okay, we're going to have a different perception of weight. Now, normally, if we're just sitting or walking or standing, that normal force and the force of gravity are going to be one and the same. But if we're in an elevator or something like that, then that normal force will no longer be the same. And we're going to feel like, if the elevator accelerates up, we're going to feel heavier. And if it accelerates downward, we're going to feel lighter, because you can imagine this, that, there's us right here, okay? If we have an acceleration upward, okay, we will still have a force of gravity being exerted against us pointing downwards. But if we're going to accelerate upwards, this normal force on us has to be greater than the force of gravity, because there has to be a net force in that direction. Okay, so our net force, if we're going to accelerate upwards, our net force, which again is the sum of those two forces, this net force has to be going up. And so that means that this force normal will be greater in magnitude than the force of gravity, and we actually feel heavier as long as we're accelerating. Now, once that accelerator reaches a constant velocity and we no longer accelerate, we'll feel our normal weight, okay, that we would outside the elevator. Okay, and it works kind of the reverse. If you're going down, there's a little person again. The force of gravity will still be what it is. Now, if the normal force is less, okay, so make the normal force less, then our net force is going to be going down, and our acceleration is down. Okay, so our acceleration will be going down as well, and we'll feel lighter than we usually do. So if we have a downward acceleration, then we feel lighter in that elevator. So conceptually, that's how that works. Okay, that's how this perception of weight, where the force normal, the magnitude of this force normal, will be less than the force of gravity. So mathematically, let's see how this works out in a couple of problems. So in this case, this is a vertical motion problem. And we have a 10 kilogram crate attached to a rope. It's rising with a certain acceleration. We want to know what the tension of the rope is. Okay, so I draw my diagram. I use the problem solving method. So I draw my diagram, and I have this. Okay, I have this rope attached to it. And I'm going to want to start to see this, guys, a free body diagram. So in this free body diagram, we'll have the force of gravity, and then we will also have the force of the tension in the cable pointing up. Now, I drew that longer because it's accelerating upwards. Okay, our acceleration is upwards, and it has a magnitude of 0.5 meters per second squared. Okay, my coordinate system I'm going to make up positive just to make things easier on us. So I want to know what the tension in this rope is. So what I'm going to use is the second law. I'm going to use F net is equal to mass times acceleration. But what I have to realize is this net force, it's not either one of those two forces. This net force will be the sum of the force of gravity and the force of the tension, and the force of gravity is pointing down. So the force of gravity will be negative mass times g, okay, plus whatever the force of the tension is. Okay, and again, that negative is there because of my coordinate system. So it's going to be negative 10 kilograms. I'm going to cheat and make g 10 meters per second squared just to make the mental math easier, plus the force of the tension. Now that net force has to be equal to the mass of the crate times its acceleration. So it's going to be 10 kilograms times an upward acceleration of 0.5 meters per second squared. Okay, and so we do that. We solve for the force of the tension, and we'll get essentially 5 newtons. A kilogram meter per second squared is newtons, so 5 newtons plus 100 newtons, which I got from 10 kilograms times 100, 10 kilograms times 10 meters per second squared, take the negative of that, add to both sides. And so the force of the tension has got to be 105 newtons. Okay, so you can use the fact that I know what my acceleration is, and I know what the mass of the crate is. I can use that to solve for the tension. I can use it to solve for a force. The other thing that you can do is you can, if we can solve for acceleration, we can then use kinematic equations. So if I have a car, okay, whoa, I went too far. So if I have a car, okay, a car with wheels, okay, and this car has a mass of 2,500 kilograms, and the engine will supply a force of 5,000 newtons. Okay, let's make this way positive. 5,000 newtons. We'll let it accelerate from rest for 10 seconds. Okay, so V naught will be 0 meters per second. And I want to know how far it's going to go in this 10 seconds. And for right now, we're going to ignore friction and air resistance. Okay, we're just going to consider this 5,000 Newton force. Well, what I'm going to do is I'm going to use F net, which in this case will be simplifying. F net is equal to mass times acceleration. I'm going to use this to get my acceleration. And then I'm going to say, oh, and I know a kinematic for distance. I know V naught t plus 1/2 at squared. So I can solve for my acceleration using Newton's second law, then use acceleration in kinematic. And this will be a very, very common technique in problem solving for you guys. So with that said, I'm going to solve for my acceleration. Okay, I'm going to solve for my acceleration. So I'm going to say acceleration is equal to net force over the mass. Now, the only force I have acting on this is the 5,000 Newton force, and the mass is 2,500 kilograms. Okay, please make sure your mass is always in kilograms, by the way, guys. You might have an evil physics teacher that gives you a mass in grams. So if that happens, make sure you change it to kilograms. So anyway, this will give us positive 2 meters per second squared for our acceleration. Now, delta r, our distance, which is what we want, V naught t plus 1/2 at squared. This is going to be 0 meters per second, so that's going to drop out. And I'm going to have 1/2 times 2 meters per second squared times 10 seconds squared, and you do all that, and you're going to get 100 meters. Okay, and so you can use Newton's second law to figure out the acceleration, then use the acceleration in a kinematic. Okay, they won't all be as straightforward as this. If I had more than one force acting here, I'd have to do this whole vector sum and figure out the magnitude, and then go to the second law. But those are just some extra steps. Okay, so a lot of what we're going to be working on in this chapter is just different typical arrangements of forces. How do we deal with something on a ramp? How do we deal with something where you have two masses attached to a string and the string runs over a pulley? How do you deal with it if you have something on a ramp attached to a rope that runs over a pulley attached to a mast? It's just different ways of analyzing. So we're going to practice that a lot. But I wanted to show you guys some sample problems and talk a little bit about the conceptual stuff with, especially like the elevator and the apparent weight. So anyway, hope you understood all this. If you have any questions, please let me know in class.